proceedings accessible to the public and to other state court judges in a couple different ways. I've told the other state court judges who couldn't make it out to San Francisco that they can listen in on the proceedings through court call. And so we've got court call up and running. I expect that various state court judges off and on will be listening in on the proceedings. But also we're doing video recordings of the proceedings through our Cameras in the Courtroom pilot project. And both sides have consented to the recording of the proceedings. Monsanto requested that we not post the recordings until the week of hearings is done, and we will of course comply with that request. And so the video recordings of the hearings will be up either at the end of the week or the beginning of next week, and I've informed the state court judges that they can access those recordings as well. So I think that's about it. The only other thing I wanted to say to the parties, for purposes of tailoring your presentation and maybe not spending too much time on the basics, is I just want to be transparent with you about what I have read and what I have not read so far. And obviously throughout the week there will be more time to do more reading in the evening. But so far I have read every expert report. I can't promise you that I've read all the footnotes, but I've read every expert report. I've read every brief that the parties have filed. I have read the IARC monograph, including the preamble. I've not yet read the EPA reports. That's certainly one of the things on my agenda to read this week. I'm trying to think. I think. Oh, and then all the. I believe I've read all the pertinent cases on causation, or all the most important ones. So what I would ask is that you please work with your experts to tailor your presentation accordingly and presume that amount of knowledge. And of course there will be opportunity in the state court proceedings to supplement the record to the extent that it's necessary. So with that, the plaintiffs can go ahead and call their first witness.
Morning again. We'd like to call Dr. Beate Ritz to the stand, please. In your honors, as a preliminary matter, we have put together books for the judges, the clerk, and for Monsanto that contain copies of her PowerPoints, the expert reports, which I understand you already have, but they're already in the book, some slides that she's going to use, and copies of important medical studies that she'll be referring to. I think it'll make it easier for everyone. So with your honors' permission, I'd like to pass those up to the clerk and your honors and to Monsanto.
Great.
Or my partner's going to do it.
First name is Beate, B-E-A-T-E. Last name is Ritz, R-I-T-Z.
We put up the CV slide. Okay. So I did not realize that Your Honor had read all the expert reports. I appreciate that. But let me just very, very briefly go through a few of your qualifications, just because I think they're important. Can you state exactly what it is you do, please?
Yes, I'm an occupational and environmental epidemiologist. I actually am tasked by the state of California in the Center for Occupational and Environmental Health at UCLA to investigate occupational and environmental causes of disease. So it's really a discipline where we teach our students and we do research that involves assessment of workplace hazards. And my specialty has been pesticide exposure assessment over the last 25 years. I've done very large studies in the Central Valley using the California registries, the pesticide use report registries, and I've worked on many different diseases, including cancer. I'm also currently the sitting president of the International Society for Environmental Epidemiology. That is a group of individuals those who professionally assess exposures. So that's how we define our tasks. And I have published more than 260 peer-reviewed papers in the area that I study, and pesticides are a big proportion of it.
Thank you, Doctor. Could we see the next slide, please? Can you explain, please, Doctor, very basically in layman's terms, what epidemiology is and some of the basic concepts of epidemiology?
Right. So I'm an MD, PhD, so I really am interested in human health. And the studies I do are really population-based studies, meaning we are assessing in worker cohorts in the population what hazards might be related to the outcomes, the health outcomes. So for occupational exposures, that is, we have a lot of good tools because workers and their workplaces are usually described well in terms of the agents they're using, the substances, how long they've been using it, etc. And that's one of the really important tools in epidemiology that we have, workplace exposures to say, well, this chemical in this kind of environment with exposure over so and so long, we can now really link to an outcome, a health outcome. So what we're doing in our studies is trying to identify either hazards or protective factors that are related to human health. So my lab is really a human lab, or better, the population of California or a worker population, and we are trying to assess whether the risk of disease in those who are exposed differs from the risk of disease in those who are unexposed. And we are generating these rates, disease rates in the exposed, and then divide them by the disease rates in the unexposed. And if that ratio is 1, we know the one in the exposed isn't higher than the unexposed, right? And so what my students learn to generate are these relative risks, odds ratios. They all measure the same thing. They all measure whether in the exposed group there's more risk for the outcome than in an unexposed group that we presume is as similar as possible to the exposed group except for the exposure. And we use different tools to do that, but generally we have different study designs that we are dividing into cohort and case control studies. The only difference between the two, with one we are starting with the outcome, cases, and we are selecting controls, and then the controls provide us with exposure information, assuming that the exposure information for the controls did not contribute to disease because they're controls, right? They don't have the disease. So they give us the rate of exposure among the controls that if the rate of exposure is higher in the cases, we then can say there's a risk. In the cohort study, we go the other way. We start with people who are unexposed, who are exposed, and then we follow them over time to see what the disease rates in the two groups are, and we again calculate our ratio measures.
Thank you. Can you explain what statistical significance is and how it is used in epidemiology, please?
Yes. So statistical significance is a very complicated but easy tool in some ways. Because statisticians have made up rules of that a 0.05 is the measure of statistical significance. However, what we are teaching our students is that with p-values and statistical significance testing, we're really just assessing whether the results of our study are how they are influenced by random noise, by random error. What we also tell our students is that random error, yes, is important. We should take it into consideration, but it is really not the most important tool we have. Much more important is that we are actually assessing systematic biases. And systematic biases are confounding, selection bias, and very importantly, exposure assessment and outcome assessment that's done right, that we get the information right. So all of these other issues are more important than just getting the p-value right, but we are using statistical significance and p-values to gauge how much random error, how much random fluctuation there is in our data that contributes to what we're seeing.
And with regard to your explanation about p-values not being the be-all, end-all, do you have support for that proposition or that you can reference for the court, please?
Oh, yes. My teacher, who wrote the textbook on epidemiology, has a whole chapter, chapter 10, that I still use with my students when I teach, in which he explains why a singular p-value is really not what we should be using. We should be using the full data that's provided in a study to us. We should use confidence intervals, p-value distributions, and really assess these data to the fullest we can, and not just rely on a p-value. We actually have a t-shirt we wear in that class when we teach it that says, "No p-value allowed."
And have you read the deposition of Monsanto's, or one of Monsanto's epidemiologists, Dr. Ryder, in this case?
Yes, I've read Dr. Ryder's statements, and they completely agree with what I just said.
With regard to p-value?
With regard to the importance of p-values.
Okay.
We use them as a tool, but they are just that. They are one tool in our toolbox, and not the sharpest.
Okay. Perhaps like me. Can we go on to potential and confounding factors? Can you explain, in layman's terms, please, what a potential confounding factor is and what an actual confounding factor is?
Right. So confounding refers to these biases, and it is one of the important biases we are trying to avoid. It comes from this concept of that we would want to know what would have happened to those who were exposed if we could take the exposure away from them. So would they have had the same disease risk if there hadn't been the exposure? That's, of course, a counterfactual. We can never know that for a group of people who has been exposed, or for an individual. So what we do is we construct these comparison groups. So the comparison groups are supposed to give us this counterfactual rate, the rate of disease when you're not exposed. But how do we know whether these unexposed are actually the right comparison group? Well, we know it by trying to judge whether there's potential confounding. And potential confounding comes in when really there are other underlying risk factors for the disease that the unexposed have, but not the exposed at the same degree. So that really the unexposed either are at a higher risk of the disease due to other factors, or a lower risk, right? We want to make them as similar as we can. So we assess confounding and we deal with confounding. The problem is there is potential confounding where we can argue whether a factor is really differentially distributed among the exposed and unexposed, or whether it's a risk factor. And there's actual confounding, which means in my study this applies. And for every single study, we have to really very carefully, and this is what I teach, very carefully assess whether the same factors should be considered confounders or not. Because you can actually muddy the pond by calling something a confounder that is not and putting it in a model. You might generate confounding, you might generate bias. So we need to use every single bit of information we have from prior knowledge to establish, first, is this a risk factor for the outcome? If not, it can't be a confounder. Second, is this factor also associated with, correlated with, influencing the exposure status? Those are two criteria that need to be present for confounding to happen. And the third criterion is that it's not, that the factor is not in the pathway between exposure and the outcome. So it can't be caused by the exposure and then causing the outcome. Those are the three principal components or criteria that we need to check off before we say it's a confounder. And it is different for every single study.
Lastly, can you please explain what exposure misclassification is, including what exposure is?
Right. So this is really what my discipline focuses on in occupational and environmental epidemiology. And I tell my students the one thing you need to learn is to assess exposures right. because when we make a mistake in exposure assessment, it is the same as if we have a very noisy room and you're trying to hear my voice. You will not hear my voice, you will not see hear the signal above the noise. So if we have a lot of exposure misclassification, it's basically information bias. We have a lot of noise, and there is maybe a true signal somewhere. There is a voice in that noise that I should be discerning, but I can't hear it. So the worse I'm doing as an exposure assessor, the more likely is that I won't hear anything, that I won't find the signal. We always think it's the opposite, that we hear voices that tell us untruths, that there's a big signal that, is a false signal. And what I really try to convey to my students is most of the time we have very poor instruments, our exposure assessment is no good, and if we see something, I actually get worried because I know if I do a bad job in exposure assessment, I won't see a thing. I will just drown out the signal in the noise.
And finally, can you explain the difference between retrospective and prospective?
Yes,
And how
so-
it applies to cohort studies and also to case control studies, please?
Right. So retrospective and prospective is really how we generate our data. And when we talk about retrospective, then we are saying that the exposure information is in the past, and we are using tools to assess what happened in the past. The simplest example is we are asking people questions, right? And they have to remember, and they have to report. So that's a retrospective assessment. A prospective assessment is I put a little monitor on my radiation worker, and over time I follow their exposures, and I also follow them for the outcome at the same time. So I follow them for health outcomes, and I measure on a daily basis with a radiation meter their radiation exposure prospectively. Of course, we have radiation meters. We don't have any tools that can actually get us this type of information for pesticides.
Okay, great. Thank you. Now let's get to the heart of the matter and talk about the relevant studies as they relate to glyphosate-based formulations and non-Hodgkin's lymphoma. So can I have that for us? Okay, first of all, can everybody see this? Is it? My screen's a little small. Okay. Can you first explain what this is, doctor, and how what it is? Just explain what it is.
Yeah, this is supposed to just be a simple visual aid. We call it a forest plot, and forest like the woods. And so really what we have in the middle, that blue line, is a stem. And that blue line reflects the null value, or the rate or odds ratio of 1, where the rate in the exposed is the same as the rate in the unexposed. So the ratio is 1, right? Same number of cases in both. So if all the red dots, which we refer to as point estimates, those red dots, if they either line up on that blue line, we would say the studies show that there's no effect. Or if these red dots fluctuate around that red line to the right and the left, we would say there's so much random noise and random variation between studies that, on average, they are null. And we can kind of guess what a summary estimate across all these studies would mean. It would mean the summary estimate would be right at having a dot right on the blue line. So then we have these lines and the whiskers, and that is what we refer to as a confidence interval. In this case, it's a 95% confidence interval, and that gives us the spread of that red dot that might be due to random error. So it's not systematic error, it's just random error evaluation. And when these whiskers are above to the right of the blue line, then they are above the 95th, then the 95th percentile is considered statistically significant. And if they go to the other side of that line, then that red dot and its confidence interval would not exclude the null, so it might indicate that there is an effect, but I cannot exclude random error. So generally what it helps us to do is see how all these red dots are actually lining up. And in this case, you can actually see that most of these red dots are to the right side. To the right side means an increased risk. To the left side, it means a decreased risk or protection. And the pattern is a nice visual to kind of gauge where most of the studies with their relative simple yes-no exposure estimate here lined up, and they lined up to the right of that blue line.
And Doctor, you teach at UCLA, University of California in Los Angeles, correct? Mm-hmm. And do you teach about forest plots and confidence intervals and in general the epidemiological principles that you teach at UCLA? Are they generally accepted in the scientific and epidemiological community?
Yes, that's exactly what I do, and we teach from the book at UCLA that my colleague actually co-wrote, Dr. Greenland, that's considered the basic textbook in epidemiology, and that I cited before with the one chapter just on p-values.
And those are the same things that you're explaining and teaching to us here in the courtroom, correct?
That's exactly it.
Okay. And I noticed that on the forest plot, there's some studies that appear to be on there twice. Do you see that?
Yes.
Can you explain why that is, please?
So sometimes it is not as easy to make a decision, because when you make a visual, you have to decide which study, and not only which study to represent, but also studies present multiple estimates, multiple dots. And you have to decide which of these dots might have the best information, the most information, and sometimes it just helps us to outline that there's more than one way to look at this data. And for example, I'm showing you the DeRoos 2005 and then also the Andreotti 2018 results, because these are major studies, and I didn't feel, even so they are on the same individuals, I didn't feel it was justified to take one out and leave the other in. It's just a foundation for a conversation about what these estimates mean.
And can you explain how the differences or the similarities between statistical significance, p-value, and confidence intervals, and how they fit on your forest plot, please?
Right, so all of these are completely mathematically aligned with each other. So these confidence intervals, the lines with the whiskers, they represent the 95% confidence interval. If those whiskers don't go across the blue line, it's statistically significant. If they cross the blue line, it's not statistically significant. However, you should not just look at the widths or where it lands, but also where the central estimate, that red dot, is. What is the direction of the effect? Because any study can be not having enough information, not having enough statistical power to exclude random error, but they can still tell you something about the direction of the effect. And that's why this is plotted in this way, because it shows you what the general direction of the effects are across all studies.
And let's look at a couple of these studies in more detail, and let's start
Before you move from the forest plot, Dr. Ritz, if I could just ask you, of these studies on the forest plot, how many of them are adjusted for exposure to other pesticides, and which ones are they?
It's a very good question. So the problem of exposure adjusting for other pesticides, actually it is the DeRoos 2003, which has the 650 next to it. That is the most highly adjusted estimate. It actually adjusts, I think, for 40-some other pesticides. And you can see that while the confidence interval could be considered wide, it still excludes the null. It's still statistically significant, and the red dot is above 2. So it's a more than twofold risk increase that's statistically significant and completely adjusted for every other pesticide. I know Anne Claire, and I would have probably argued with her about this approach, not thinking that she should have put 40 pesticides in there, because that's not how I teach my students. I teach my students you have to really consider whether any one of these pesticides is a risk factor for the outcome. If it's not, you shouldn't put it in the model. If it is, then we can discuss whether that pesticide also is related to the one under investigation, glyphosate in this case, meaning do the two pesticides really correlate with each other, or does one imply the other is also used? And if that's not the case, then again, we should not be throwing this into the model. However, she went all out and threw them all in the model, and the effect estimate is still statistically significant.
Can I ask a clarification question about that? I think you said that you shouldn't include the pesticide in the model. You shouldn't adjust for the pesticide unless you know it's a risk factor for NHL.
Yes,
that
that's
right?
correct. That's the first rule of assessing confounding.
So, but what if you don't know whether the pesticide is a risk factor for NHL?
Right. Then
That in an epidemiological study?
if you don't know, you have to think about what you do when you put this. Then you would say, I want to try out what happens when I put this in my model. However, you then have, when that model then shows a different effect estimate, we have to discuss what that means. So, for example, smoking causes lung cancer. I don't think we want to argue about that, right? But somebody has a brilliant idea where they say, okay, I really think it's not smoking, it's breath mints that cause lung cancer. So let's ask everybody also whether they are chewing breath mints. And let's now say that 90% of all smokers take breath mints because they want to get rid of that odor. And when you then say, okay, shouldn't we put breath mints? We don't know whether it causes lung cancer. Shouldn't we put it in the same model? What will happen is that the effect for smoking on lung cancer will halven. By definition, because you are now putting two highly collinear variables into the same model. Whether that means now that breath mints cause lung cancer or not, or breath mints are just an indicator, a proxy for smoking, you have to decide. So we have to decide for every single pesticide whether it is truly a risk factor for the outcome, and we should consider it as a potential confounder, or it's an indicator for having used the pesticide under consideration. It's just coming along. It's a rider.
So your opinion is that if we don't know a pesticide is a risk factor for NHL, we should not adjust for it in a study?
That's not, sorry if it came across wrong. No, I'm not saying we should not adjust for it, but when we adjust for it, we should really be careful about how we interpret what's happening to the effect estimates. Most likely is that the confidence intervals widen when you do this, and that the effect estimates, if that pesticide is highly correlated with the one under investigation, it is you who has to decide whether it means it's a confounder, it's a true risk factor, and I should adjust for it, or it's a proxy like the breast mint, right? And nobody will take that away from us. We just have to do that.
And you mentioned DeRusse 2003. Are any of these other studies adjust for other pesticide use?
The Erickson study adjusted for other pesticides, but the estimate I'm showing here, I don't think is the adjusted one. No. So that's actually where it happened, as I recall. Where when you put one or two other pesticides that are highly correlated with the actual glyphosate pesticide, then that red dot goes to the middle. It's 1.5 instead of 2.
And so why did you include a portrayal of the Erickson study on this forest plot that did not adjust for pesticides? when adjustments had been made in that study for pesticides.
Right, because the pesticide they adjusted for, MCPA, was one that was used prior to glyphosate, and glyphosate was the one that followed up, that was replacing MCPA. So we have exactly a situation where you need to decide whether you believe that MCPA is a true NHL causative factor, or it's just that breast mint that tells you, well, they used MCPA, then they, had a new agent that they thought was working better, glyphosate, so they replaced MCPA by glyphosate. So MCPA is just an indicator for later glyphosate use. So you have to make that decision. And I didn't see a literature that told me that MCPA was truly an NHL risk factor.
And any other studies on here adjust for other pesticides?
Yeah, DeRoos and Andreotti. DeRoos 2005 and Andreotti. Mm-hmm. AHS, yes. Mm-hmm.
What about
What about McDuffie?
McDuffie, I don't think the one I'm showing is adjusted.
So the McDuffie did adjust for pesticide use, but your portrayal of the study does not include an adjustment for pesticide use. Is that right?
Other types of pesticide, yes,
Okay.
yes.
And what about the KNAP study, if I may jump in? Is that adjusted for other pesticides as well?
As far as I know, yes.
That's
oh, wait,
one other.
the one I portrayed didn't, but they later showed also an adjusted one, yes.
And that shows an elevated odds ratio after you adjust for pesticides in the KNAP study, correct?
Yeah, it depends. Actually, there are different ways to do this. Some authors like to just throw every pesticide in the same model, and some authors just use one after the other. And you then have to decide which estimate is the one that you want to present or you want to talk about. But they're trying it's called sensitivity analysis. They're trying out, well, what happens if? So they are sometimes using one pesticide because they think it's maybe the more convincing one that could have an effect on an NHL, and then another one because it's a common use or it's a very toxic one, and they want to see how these effect estimates change. That's actually how we're testing our data, how much changes when I do one thing or another.
So I should move this into evidence. It's Exhibit 297 on our exhibit list. And
Admitted. And have you, by the way, have the parties stipulated to the admission of all these exhibits in advance? Okay, so then if it's something that you've worked through together already, you can just do the mechanics of getting them admitted afterwards, so we don't have to spend the time doing it.
okay, I will do that, Your Honor. Okay, so going back to the DeRoos study for a second, you mentioned that it was the most highly adjusted and that it was an elevated odds ratio and statistically significant after the adjustments. Is that correct?
Yes.
And approximately how many pesticides did the DeRoos adjust for as you've indicated on the forest plot?
I understand it's some 40 plus pesticides.
And for each of these studies, did you look at and consider the methodology that was employed by the authors of the study?
Yes, definitely.
How did you go about doing that?
Well, you want to know how the study design, first of all, you ask what the study design is, but then you also want to know how the actual study was conducted. And so what you want to know is whether the disease assessment was properly done. And just about all of these studies had very high, very good disease assessment with cancer registries and pathology. So I didn't see any problem in that regard. And then, of course, the second most important thing is how the exposure was assessed. And generally, all of these studies are using interviews. None of them were able to assess biomarkers or any kind of records, except that McDuffie actually went back and asked farmers whether they could go to the suppliers and ask the suppliers about the purchasing records for pesticides, and then compared the purchases for the specific farmer and what the farmer had told them to the purchasing records. And they found that they agreed very strongly. And where they had disagreements, they were able to actually rectify the disagreements because the farmer that year had bought the pesticides somewhere else or not applied them. So that is a very nice tool to use, going back to records, but not everybody can do that. Then if it comes to interviewing, you really have to consider how the interviewing was done. Was it done in person, face-to-face? Did people go to the homes of these people, give them a chance to look at their purchasing records, spend time with their partners to discuss what they had done in what years? Or did you just give them a questionnaire that you gave them half an hour to fill out? And that makes a big difference. There are case control studies with maybe 400 cases and the same number of controls where home visits are done and these individuals report on their use of pesticides for hours in a very interactive way with the interviewer. And I would consider that a much better exposure assessment than giving somebody a sheet of paper with 20 pages and say, well, in the next 20 minutes, please report, right? So that's the way I would assess the exposure assessment in these different studies. And then the next thing is how much did they then also ask about lifestyle factors, other pesticides, other possible risk factors for the outcome, such as family history of cancer, and then how did they bring all that together in their analyses, and are the analyses done adequately with the data at hand, and then also interpreted in a sufficient way.
Let's go to the 2002 Hardell study, please. And you weren't asked a lot of questions in your deposition about specific methodology, but Monsanto has attacked the methodology of some of these studies, so I want to walk through some of the methodology in the individual studies, okay? How was the unexposed group defined in the 2002 Hardell study?
Right. So the Hardell study is one of these typical case control studies. It was a Swedish study, and Sweden, just like all the Scandinavian countries, has exceptional record systems for health records as well as for retirement and occupational records. I actually have a large study that's NIH funded in Denmark because of that reason. We are all jealous of the Scandinavians. So they are using these beautiful record systems to identify cases, and they also have population registers from which they can pull the names and addresses of unaffected people. That's called a population-based selection of controls, very well done. And then they go and interview these people about their exposures. When it comes to the analysis, so I didn't have any problems with any of that. When it comes to the analysis, you are now asking yourself, well, what happens, because we know farmers don't just, farm one crop. Most farmers don't just farm one crop, but even if they do farm one crop, they may be using different herbicides because whatever they are the pest they are trying to get rid of, the weed, may get resistant, or they might have received recommendations to alternate different pesticides over the years to not make the weeds resistant. So generally, when you ask a farmer, they use more than one agent. It's not like in industry, like my radiation workers, where the one exposure they had was radiation. Here we have a mixture of exposures. So when we want to compare what any singular chemical does to an outcome, we have to consider the co-exposures, but we also have to consider what is the true or the correct comparison group to use. And what Hardell chose, and later Erickson as well, was to say, well, what happens if we are comparing the glyphosate or phenoxyherbicide exposed individuals to controls that did not use pesticides? So these are community studies. This is not like the AHS where everybody was a farmer who actually applied pesticides. This was done in communities. Some people were farmers, others weren't. And the critique often is that, well, you're comparing farmers with farmers. If your farmer doesn't use glyphosate, he probably used DDT, and that's also a carcinogen. So you're comparing people who are exposed to one carcinogen to people who are exposed to the other carcinogen. If you don't see anything, that's because they're all exposed to some carcinogen, right? So what they tried to do here is exclude anybody who had any pesticide exposure from the comparison group and say, now we have a clean group. We have a group of individuals who have glyphosate exposure with or without other types of exposure, but we are comparing all of them to people who never used pesticides. Sounds like a good idea, is not such a good idea. And I try to explain that to my students, because what we do when we get a little more technical, we call it a collider bias. And I explain that to my students what it is, but then I also say, well, yeah, collider bias is a kind of selection bias, and you should not generate this selection bias by excluding, in this way, people who have other types of pesticide exposure from the control group. But then I keep going and say, well, this is a potential bias, right? And they generated this potential bias. But the next step is to assess what is the quantity of that bias, because we are a quantitative science. We're not a qualitative science. We want to know how big is that bias. And now let's estimate how big that bias would be. And it's pretty simple to do in this case. All you have to do is add the controls back into the comparison group who they excluded. And they actually gave you a few tables that showed that data. And I was able to put that back in, redo the calculations, and convince myself that the change in the estimate that they are representing is within about 10% of the estimate. So the quantity of that bias is minimal in epidemiologic terms. Yes, there's bias, but it is minimal.
And I should have mentioned that the Hardell 2002 is Exhibit 20, and Hardell 1999 is Exhibit 19. And Erickson 2008 is Exhibit 17. And I will mention the exhibits beforehand. My apologies to the clerk and the court. Okay, so then let's talk about Erickson 2008 for a minute, which is Exhibit 17. Did Erickson 2008 analyze latency periods at all? And can you explain a little bit